recording. Good, good. So, how's everybody? Any thumbs up? Everyone's good? I hope you guys are all right. The quiz 2 results, you guys are doing outstanding. I think the class average is in the 90s, so I think you guys are ready. Morning, Raf. The next quizzes and all these, you guys are doing outstanding. So what we're going to do is we're going to ratchet it up a little bit. Okay. I think the class average was, I don't know, in the low 90s. So you guys are ready there. You guys are good to go. So there's nothing due there this week. You guys have the week to relax. The next week there, week 7, I think we have our quiz 3. Okay. And that'll be on bone and muscle only. And yeah, guys, just a reminder there, if you guys could keep your side on mute, and if you have any questions, just shout them out, and that's how we'll do it. But that's our plan, and everything is going according to plan. All right, so if you guys have anything to add, or if you have any questions, let me know. Shoot me an email. But other than that, I think we're doing really well. Okay? So that is the plan. So let me, there we go. Let's go share. And PowerPoint. So there we go. We are on track. My goodness, apologies there on the late start. It's just one of those mornings. My daughter she has a cross-country track meet, so she had to be ready to go and out the door by 10 after 8, or had to be there for 10 after 8. And then my son had to go at normal time, so everything is, it is very cold, so please make sure that you dress appropriately. All right? Yeah, I didn't see any questions. You guys are quiet. Everything looks great. So let's go. And for any of you people here who are watching this after the fact, you're doing great. If you're working there during this time, well then thank goodness these videos are being recorded. Just don't change whatever you're doing. Everyone's doing pretty good. And I just want to let you guys know, I said with this morning's announcement, I added in there that next week there will not be a live class like this one right here. Like I'm live, I'm living and I'm breathing, and I'm recording this as I breathe. But next week there, what I'll do is I will pre-record a screencast. Exactly the same thing. Won't look any different. Okay, it's just that I won't meet you next Wednesday. What's that? October 16th at 9 o'clock. I have a doctor's appointment there for my son at an eye appointment there with an ophthalmologist there in Toronto next week at 10:30 in the morning. So I can't make this one, but that's okay. You guys will be fine. I'll let you guys know what's happening as far as the quiz goes. Really no difference, so we're doing all right. And I see there that you guys, some people have already uploaded their assignment. Congratulations, you know what I mean? You're doing great. So just let me know if you guys have any issues. But as far as I can see, I think we're doing okay. Okay, let's go. So last week there, we introduced our second organ system, first being skin. Last week there we did bone. Okay, and the natural progression of things is we move on to muscle. Okay. Bone, muscle, they kind of work together, right? The whole idea of movement, coordination, these kinds of things, okay? So we are just doing great. Let's move it, shall we? So we're going to look at the 3 types of muscle, okay? And there are 3 types. Maybe you didn't know it, maybe you did, okay? We're going to compare the structure of the whole muscle and right down to the muscle fiber. We're going right down to the molecular. You know, the whole idea there that, a muscle contracts. Now, you look at the word contract. It means to shorten. And you think there for the bicep, in order for it to function, it contracts and pulls my arm away, right? And if my arm wants to go the other way, now it's my tricep contracts, right? So this whole idea there that the muscle shortens, well, it actually does that at the molecular level. And we're going to show you there. It's called the sliding filament theory, okay? And, you know, every time a muscle contracts, okay, that's its function, right? But then it has to reset in order for it to contract again and again and again. Well, you look at these muscles right here. I don't know if the camera is good enough to pick up, you know, how fast they're moving. But you think about how these muscles are contracting and resetting so quickly, all right? And we'll look at all the different kinds of muscle, and we'll look at muscle in different ways. Yeah, there's 3 types of muscle, but I also want you to see muscle as white meat and dark meat. You know, like think of it as a chicken. And if you didn't know this, when you eat meat, you're eating the muscle of the animal. That's what it is. Might turn you off meat for good. You know, beans. There's a great protein replacement there for muscle. And by the way, the great meat, it's a great source of protein, but it's not the best source of protein pound for pound. And the greatest source of protein pound for pound, peanut butter. Interesting, eh? We'll get more into that as we go. We'll look at calcium. Okay, the mama always said there, you drink your milk, eat your cheese there because it's good for your bones and your teeth. Well, mama never told me there that, yeah, calcium is good for your teeth and your bones, but it's no muscle would fire. No neuron would fire without calcium. So this is mucho bueno importante. It's very important to have this one here. And we'll talk more about that there. We'll look at ATP involved in muscle contraction. And we'll look at describe the relationship there between skeletal muscle and nerve. Okay, we're going to look at the motor unit, the neuromuscular junction. The whole idea I know we haven't done nerve yet, but you're getting it right now. A little bit of it, okay? So the whole idea, the neuron, the message gets sent down a nerve, and the nerve actually touches a muscle and ignites the muscle per se, okay? We'll get more into that as we go. Let's go. 3 kinds of muscle. That's what we're going to look at right here. Okay, you've got skeletal, smooth, and cardiac. And let's go. Skeletal muscle. Okay, only muscle that it's voluntary. Okay, I have control. I can move my neck. I can move my arms. I have control over this. Somatic nervous system there. I have control over it. Okay, long striated cylindrical fibers there. Multinucleated. They can have multiple nucleus within a cell. Considered there the meat of the animal. Okay, now you look at this. These are the things there I want you to know from skeletal. It's voluntary. Okay, I have control over it. It is very strong. Okay, you know what I mean? Arnold Schwarzenegger can lift hundreds of pounds. All right, so it's voluntary, very strong. Okay, but doesn't last long. You know, like how many bicep curls can you really do without, you know, before you suffer fatigue? Okay, and then, you know, if you could do 20, 30, or 40, even if you could do 50 bicep curls, whoopee ding dong. It's not a long period of time. And we'll talk to you about long periods of time when we get into the other kinds of muscle. Okay, so voluntary, strong, doesn't last long. The smooth muscle, you can see here, it's quite different looking. Okay, there's the electron micrograph there. You can kind of see it. Okay. Now, what I want you guys to know about smooth muscle is this is the muscle there that, you know, like when you eat a banana, you chew it up and you swallow it. You don't, what happens to that banana? I don't know. You know, I don't see it again for another 36 hours, right? And what is moving that banana through my digestive system? The whole idea there that there's this whole autonomic nervous system there that we don't have control over, okay? And it's all automated. And the whole idea there that when you swallow that banana, there's a motion there called peristalsis. I'll show you guys that there later. And this is, now we're talking about smooth muscle, which is basically the complete opposite of skeletal. Remember, skeletal was voluntary. Well, this one here is involuntary. You have no control over that banana. Okay? And here we're talking there of the esophagus, you're talking the stomach, you know, when you get hungry and you're, as my son would say, Dad, I'm hungry, my tummy's wiggling, right? You know, and moving that food down through your small intestine, large intestine, all these kinds of things. It's all smooth muscle. So smooth muscle is involuntary, no control, not strong. Doesn't have to be. It's pushing bananas around, right? And it lasts a long time. Okay? The whole idea there, this muscle there, it can do its thing for hours. Okay? The whole idea, the digestion process, you know, the stomach moving the food in and around, okay? It can sit in there for a while, absolutely, okay? So complete opposite of skeletal. And then we have cardiac, and here we're talking about the heart, okay? It's a combo of the previous two. You can see there it kind of resembles skeletal, but it has these branching. You see how it branches? And that's because every single cell of the heart is connected in some way to every other cell. And we have our pacemaker in our heart. Zzz, okay, and it ignites the heart and allows for the heart to beat. Well, that's the whole reason there for this branching, is that there's an electrical conduction that's initiated in the pacemaker, okay, which we'll get into. I don't want to get into it too much right now, but it's ignited, and then that electrical discharge goes all the way through the heart and contracts. So that's why these guys here, they have this branching. But cardiac, involuntary. Why would you want to have control of your heartbeat, right? Okay, so it's involuntary, very strong. Okay, like that, the heart, when we get into it there, you'll see that the heart pumps the blood out the aorta. Okay, the biggest artery, okay, in the body there. And do that for as many times as you can. You probably can't do 30, but the aorta takes a whack every single time. The heart takes a whack every single heartbeat, and it's still there. So the heart is very strong, involuntary, and lasts a long time. Okay, so just a bit of review there. Okay, right in here, you've got there's your heart, your cardiac. You can tell by the branching. You see the differences there between skeletal muscle, and then here's your smooth, which looks completely different. So skeletal, voluntary, strong, no last long time. Smooth, involuntary, not strong, lasts long time. And then you have cardiac, which is involuntary, very strong, lasts long time. Okay, good. And we will look at these there. And as far as getting into the microbiology of muscle tissue, this is where we're going to focus at right there. We will come back to heart there. I don't know, is it week 7, week 8, somewhere in there? Okay. Yeah. No, week 7 be blood lymph. So yeah, you're after reading week there. We're good. Okay. So just some words here to look over, because we're going to be hitting these sooner than later. You've got a muscle fiber, and we are going to go pretty deep into this, okay? And some of this stuff here, you're going to go, whoa, but it's all part of the game, okay? And just remember there, you don't have to memorize any of this. You just got to dig for it in the PowerPoints, okay? So we're going to look at what exactly a muscle fiber is. The skeletal muscle fibers there are formed by the fusion of these multiple myoblasts there during development, okay, and they have multiple nuclei, okay. It's all about protein synthesis, protein, 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 right? Remember, you need your daily source of protein. You got to get it. And if you're a vegetarian, perfect. Then you're eating beans, all right? Eggs, cheese, these kinds of things. All has good protein. They're striated. This whole idea there, getting back, and we'll show you right here. You'll see there, zooming in, you'll see there that the skeletal muscle, you'll see this striation, red, white, red, white, red, white. Well, that's exactly what's going on here. Contraction, reset. Contraction, reset. We'll get more into that there. Yeah, you know what I mean? The rest of it there I'm not too worried about here. But you have a look here. Fibers are the longest cells in the body. Some of them there, like the sartorius there, they can get, you know, into the centimeters long. Okay? Held together there by connective tissue and enclosed in a fibrous sheath called the fascia. You know, when you eat a piece of chicken or something there, you can, you know, you're pulling it apart. If it's uncooked there, you can actually see this fascia. Okay? Some fibers contract quickly. Others do not. We'll come back to that. Think white meat, dark meat. White meat, dark meat. It's muscle, it's muscle. Skeletal muscle, skeletal muscle. But there's a big difference, right? Dark meat looks dark. Why? White meat looks white after cooking. Why? What kind of muscles are these? What is their function? We'll get into those. Generally there, smaller the fiber, the faster the contraction. And you'll notice there that your fingers are moving. You move your fingers there. Where are the muscles that's doing that? They're down in here. You can feel them. Okay, we'll get there. Exercise can increase the thickness of muscle, but doesn't make more. Interesting. Skeletal muscle has some defining characteristics. Multinucleated, contains mitochondria. What do mitochondria do? Just trying to think here. Oh, are those the powerhouses of the cell? They are. We're going to look at myofibrils. We're going to look at sarcomere. These are all great words. Always good to know there that muscles are attached to bone via tendon. Tendons connect bone to muscle. Ligament, bone to bone. Ligaments aren't supposed to move. Like the whole idea, if you sprain your ankle has all these ligaments there, and that's cement. And those joints are not supposed to move in that direction. But if you sprain your ankle, what you're doing is that ligament stretches. And if you don't get off your foot for a couple weeks and allow this thing to heal properly, what will happen is it will heal stretched. So if you don't take care of that sprained ankle, that joint will be loose for the rest of your life. Okay? And so yeah, be careful. Just take care of injuries. So just remember, tendon, bone to muscle, ligament, bone to bone. These guys here are involved in movement. And fingers move because the muscles in the forearm and a few tendons there in the finger. Perfect. Muscle terminology. Fascia, connective tissue that holds muscle fibers together. Fiber is an individual muscle cell. Insertion and origin. These two are opposites. Okay? And here we're talking about the ends of the muscle. One end of the muscle will move bone. The other end will be an anchor. The whole idea. Okay? One end of my bicep is pulling my forearm. The other end of my bicep is anchored to my shoulder. Here we got these words, insertion and origin. Okay? Insertion is the more movable end of the muscle. The origin is the anchor. Okay? Good stuff. We'll come back to that there. I have some good picture slides. I haven't shown you any pictures yet, but we'll get there. There's your ligament. Okay, bone to bone. Motor nerve. This is where a neuron meets a muscle cell. Okay, that's what we're getting for. That's where we're getting to. Myofibril. Fibrils in the muscle cell, they contain myosin and actin, which we'll get into. And the whole idea of a muscle contraction, it's these guys right in here. These are your myosin and actin filaments, and they sit beside each other. They kind of touch, but they don't. And contraction, and then reset. We'll get there. So you have myosin and actin, thin and thick filament. We'll get there. Sarcoplasm, related to cytoplasm, you know, the jelly-like matrix there that's within a cell, but this is a muscle cell, so we call it sarcoplasm. Sarcomere, that is the contractile unit of the myofibril. And this will all come, you'll hear these words again there in about 2 shakes of a lamb's tail. So there's your tendon, okay, that is muscle to bone for movement. Muscle tone or muscle tonus. Now, the whole idea there is we're all sitting down, I'm having a coffee, I'm relaxed. And my muscles, I'm just feeling my quadricep, my leg muscle there, it's darn near asleep. I'm so relaxed. I'm squishing it. My muscles are completely relaxed. But if all of a sudden a raptor, dinosaur, or a rhino shows up right there and it's looking to tromp me, or eat me, or beat me, or whatever it is, you see, this is part of the evolutionary aspect of how amazing the body is that our muscles are always in a state of what we call muscle tonus, where they're always ready to go if need to. Even though I'm relaxed, but in a second's notice, if your life is in danger, boom, those muscles can be ready to go, and I mean run you 5 kilometers if you need to. Okay? It's a state of tension that always is present in muscles, even if we're relaxed in a relaxed state. We'll go talk more about this there in a bit. Fibrillation, spontaneous contraction of random groups of muscles. Sometimes there you'll feel part of your leg muscle or twitching or these kinds of things. Heart fibrillation you really don't want, because then it now screws up the heartbeat. But we'll get more into that as we go. So let's get on to the good stuff, shall we? So, zooming on in here, you'll see that this is kind of a macro view. You see there's your bone, there's your outer covering of the bone, periosteum. Okay, there's your tendon there that connects the bone to the muscle. Okay, it's kind of a macro view here. Okay, and you'll see that there's your muscle. There's the outside covering of the muscle called the epimysium. Okay, and then you'll see within the muscle here are these what we call fascicles. Okay, and if you pull one of these guys out like we just did right here, you'll see there that it has its own covering called a paramecium. Okay, and then if I can pull one of these guys out here, these are the muscle fibers. Okay, and this whole shot here I've blown up right in, you can see here, I've blown it right out. There's your paramecium, there's your paramecium fascicle, and that's what's going on here. So we'll start here. Okay, and then we move on to here, and see there's your paramecium, the covering there for each of these fascicles that's in there, and you'll see there that it's at this stage there that the blood starts to enter. Okay, not at the in this stage up in here, but once you pull out one of these fascicles there, you'll see there that these are the fascicles here, and within the fascicles you have these muscle fibers, as you can see right here. Okay, and then you pull out of these muscle fibers what we have myofibrils, and you'll see there that it's at this point that you start to see that striation. Remember there from the red, white, that's what you're looking at there, and you'll see that now we're getting into what's called a sarcomere. We'll show you this there in the next slide. Okay, so epimysium covers the muscle, the outside, okay, and then you pull the fascicle out, there's your paramecium, okay, you pull out one of these guys, it's a muscle fiber, and you see it multinucleated, you see the nucleus of these guys here, and I'm in the way, there we go. So you'll see that the epimysium, paramysium, and then these muscle fibers have what's called an endomysium. That's the last one. Okay, that's the covering there for a muscle fiber. All right, and then underneath there you'll have the sarcolemma. Now this is that will come into play, the whole idea that a neuron sends a message, and it touches there a muscle, and it sends the message along the sarcolemma. That's what charges the muscle. Okay, it runs along there. Okay, in between these myofibrils in here, you have what's called the sarcoplasm. Okay, just similar there to cytoplasm, just a matrix there to move things from A to B. Okay, and then you pull one of these guys out, it's called a myofibril. Okay, and you can see that striation, and then you pull one of these guys out. This is always, oh dear, oh, I hope that wasn't the doctor. All right. But anyway, you know what I mean? You miss those doctor calls, you never get them back, right? But I don't think it was. I didn't recognize the number. So you pull one of these, what we call microfilaments out. And then that microfilament there, you see we zoom on over here. And this is the same thing there, okay? These are one of these microfilaments, okay? And you can see what's going on. Now, heavy stuff. So have a look here. This is what we call there the sarcomere. Okay, and you can see what's actually going on here. You've got this thick filament. Okay, and then you've got these thin filaments. And that's what's going on here. Here's your sarcomere. All right, and just going back into here, you remember these guys? Okay, from here to here and then here to here. That's your sarcomere length. Okay, and I'm not interested in Z lines and all this kind of stuff, but you see there's your sarcomere, and this is the contractile machinery that makes your muscles contract. Okay, now you'll zoom in here, you see this thick filament, it has these heads. Okay, and when a muscle contracts, those heads will bind to the thin filament and kind of pull their way along until the sarcomere's length shortens. Okay, those thick filaments there, they bind, and it's called cross bridging, and they come across like this, and then it will reset to do it again. That's it. That's how these muscles contract. Thick filament, and then your green thin filaments there. Just another shot of it here. I'm just going to zoom out because I had, what's going on here? There we go. So you'll see the same thing. And you'll see A bands, I bands, H bands, Z bands. I'm not interested in any of that. Okay? I'm just interested in, you see there, the thin filament. The green lines right in there, the thin filaments are actin. The thick filaments with the heads, these ones here are called myosin. Okay? And again, you'll see there this artist depiction there of what's going to go on. So you got the thin actin filaments, the thick myosin filaments, and these guys here, they contract when the muscle is ready in the presence of calcium. If you don't have calcium, none of this happens. That's how important a mineral this is. Okay, so in the presence of calcium, those heads on the thick filament will bind to the thin filament there and pull its way along and contract. That's what's going on there. Just another shot here. Just blowing it up again. You know, a bit of overkill. It is kind of heavy stuff. Okay, but what's important here, the three different coverings within the skeletal muscle itself. There you have the fascicles, and then within the fascicles there you have the muscle fiber. Okay, there's your muscle fiber here. Within that you have the myofibrils, and within a myofibril you have these individual muscle filaments. Okay, and that's where you find the actin, thin, myosin, thick filaments. It's okay? Have a read at it, pause it, have some fun with it. It's good stuff. You'll see it again on the quiz for sure. Okay? So, let's have a look here. Myofibrils are bundles of contractile filaments that give skeletal and cardiac muscle their characteristic striated appearance. You remember there's a bit of a relationship there between skeletal muscle and cardiac. Okay, cardiac's involuntary, goes till you're 99. Skeletal muscle tires in about 5 minutes. All right, but you'll see there that they have that striation, red, white, red, white. That's because of actin and myosin. Okay, those the thick and thin filaments. There are these videos here that I'm not going to play, but pause the video, watch this. These videos here are awesome. You'll also notice there in the folder there on Blackboard, I posted, I don't know, was it 5 or 6 or 7 videos. They're eating up all this space on Blackboard, so probably in a couple of days I will remove them. So what I want you guys to do is all those videos there that I posted, download them, okay? Because they're mint. They're heavy, but they're good, and we're going to talk about these there. So this is a really good video, okay? Have a look at it, okay? And yeah, watch it. It just a nice little introduction, takes you through, okay? The videos, normally I would play them in class, but these videos here, they really add to this particular week 6 muscle idea. Okay, so moving on. When a muscle contracts, the whole thing shortens because these individual filaments slide across each other. But the thick and thin filaments themselves do not shorten. It's not like, you see the thick filament here, the myosin, it's not like it gets shorter. You'll see there the thin filaments there, they don't get shorter. They just kind of move across each other because you'll see there, and there's this space, okay, for, and there's these spaces in here for the thick filament to move into, and this space here for the the thin filament there to move across, okay. There's another video here. This isn't a video. You'll have to go to the Blackboard, but the same video is there. And it shows you the whole idea of how calcium allows for muscle to contract. If you don't have calcium, you don't have any muscle contraction. Zero, zip, nada, nothing. Okay? Only in the presence of calcium will these heads. See, this is the thick filament here, the myosin with the heads, and here's that thin filament, the actin. And if you go back in a resting stage, okay, you'll see there that these heads are not bound to the thin filament. In a resting stage, they're not, because your muscle's not contracting. I'm sitting here, my legs are not contracting, they're relaxed. This is what they look like. Some of the heads, though, a very small percentage of those heads will be bound. And you remember that word muscle tonus, tone. That if we're just sitting here relaxed, but all of a sudden our life becomes in danger, our muscles, boom, are ready to go, always. So some of these heads are just attached in case of a raptor or a dinosaur or a hippo running after us while we're asleep. But when a muscle is fully in contraction, all of these heads will be bound, okay? But remember, only if you have calcium in your system, okay? Because if there's no calcium, these heads do not bind, so therefore if you don't have any heads bound to the thin filament, then you do not have muscle contraction, okay? Good. So this is a great video. Go and have a look at this one there on Blackboard. Okay, the whole idea here, there's this, for the thick filament, this head is bound to the thin filament. So therefore now, it can pull itself and contract, but only in the presence of calcium. Okay. This is a good slide here. This is what we call the neuromuscular junction. And you'll see here there that what we have is a neuron, okay, sending the message, right, from the central nervous system there out. And here, I want to give you a thumbs up. You see, I mentally said that. The message was sent from my central nervous system, and therefore now I've given you the thumbs up. Okay, now how does all this happen? Well, the neuron sends the message down. Okay, and you'll see there that I'll kind of zoom in here, do the best I can. This is your neuron here, and the message travels down. And you'll see that the neuron doesn't at all touch the muscle. You'll see that there's this gap in between, and this is your muscle here. All right, so and this is what we call the neuromuscular junction. All right, and what happens there? The message travels down, and as the message travels down, again, calcium is involved. If you don't have calcium, that message ain't going. Okay, so anyway, the message comes down, and acetylcholine, which is a neurotransmitter, because you see, one neuron never touches another. One neuron never touches the muscle. There's always a bit of a gap. And again, that's an evolutionary trait. We'll get more into that there later when we move on in the course. But you'll see there that the purpose of these neurotransmitters like acetylcholine, serotonin, dopamine there is to send the message that just came down here, but these guys don't touch. So how does that message get across? The neurotransmitter gets released. Okay, and then there are receptors there on the muscle side of things. They receive that neurotransmitter, and then all of a sudden you'll see here, remember the sarcoplasm where the electrical discharge runs along the muscle fiber? Okay, and then all of a sudden now the message comes down, neurotransmitter comes across, and that message is then cascaded into the muscle. And then the message travels along the muscle, okay, along the sarcolemma. But muscles are pretty deep if you're talking microbiology, right? You just can't have an electrical conduction traveling along the sarcolemma, the outside layer of a muscle. We got to get into the muscle and ignite those muscle cells, right? So how does that happen? Whoop. We have these what we call T-tubules. And you'll see there that this electrical discharge and goes down. And it goes down deep into the muscle. And look at that. There's your calcium. So that electrical discharge goes down. In the presence of calcium there, those heads from the thick filament will bind to the thin filament, and then you'll have muscle contraction. That's the whole thing. Yeah. I'm just making it, I just said it in 2 minutes, but now you guys have to kind of try and understand it. Again, try it one more time. The message comes down, okay, the neurotransmitter is released into the neuromuscular junction. The neurotransmitter then, acetylcholine, has receptors there on the muscle side that receive it, and when they receive it, that same message is then traveled along the muscle sarcolemma, and then down a T-tubule into the deep parts of the muscle, but only in the presence of calcium will those heads bind, and you'll actually have a muscle contraction. Interesting stuff, eh? Maybe not so much. Let's have a look here. The impulse stimulus brought to the muscle by the motor nerve by way of the neuromuscular junction. The neuromuscular junction is a connection there between the muscle cell and the neuron, which contains acetylcholine. Okay, that's your neurotransmitter. There are many of them. Okay. The presence of calcium ions causes acetylcholine to be released from the neuron and bind to the acetylcholine receptors on the muscle cell. Heavy stuff. This is where we're going. Okay, but you guys are ready. You guys can do this. The motor nerve fiber divides among the thousands of muscle fibers. So one nerve fiber supplies 5 to 200 muscle fibers. So one neuron, okay, one nerve fiber there supplies the electrical conduction there, the message there for anywhere from 5 to 200 muscle fibers only, okay, which penetrates the sarcolemma to form what we call there a synapse, okay. Here's a disease there, myasthenia gravis there. Abnormal neuromuscular junction activity causes muscles there to weaken. Okay. Here's another movie there. This isn't a movie, it's just a screenshot of what's going on, but this is there, the function of the neuromuscular junction. It's a really good one. And just by the way there, if you go on to YouTube and you just look at McGraw-Hill, okay, they'll have lots of these videos. And these videos are great. They're like a minute long. You know, there's all these videos there on YouTube. They're a great one there, Crash Course. Great. The guy talks like a million miles an hour, and the video is like 10, 12 minutes long. It's too long for, you know, I want to learn a concept, 1 minute in and out. So that's why these videos are great. So please make sure to download them. They are mint. Okay, so this is just like a 1 minute video on that right there. Good. So muscle contraction there, calcium is stored and is released following membrane excitation. Now it doesn't matter where you want to start here, and you'll see that the whole idea in the presence of calcium, you see on the thin filaments, on the actin, in the presence of calcium, okay? Because right now, without calcium, these heads don't bind. But in the presence of calcium, what happens there, okay? The calcium alters the shape of the actin thin filament. Because if there's no calcium, those heads are blocked from activating, from touching there the thin filament. But in the presence of calcium, okay, it distorts the thin filament and allows these heads to bind. Okay, that's what's going on here. And only in the presence of calcium can these heads bind. Okay, and you just have a look here, there, the whole idea, yeah, that's all I'm looking for there. Just wanted to show you that in the presence of calcium, the thin filament changes shape. Without calcium, it's just in a kind of a dormant state, and you'll see these lines on here. Without calcium, those lines are blocking, okay, these sites here, and that's where the heads want to bind. But if they're blocked, they can't. But in the presence of calcium, these receptor sites there are opened up so that the heads can bind. Okay, good. The role of calcium and adenosine triphosphate here. So calcium is stored away from the thin and thick filaments in the sarcoplasmic reticulum. Okay, so calcium is stored. It has to be. Okay, because we need it all the time. When stimulated, though, the sarcoplasmic reticulum there releases the calcium. So the sarcoplasmic reticulum is just a place where they hold the calcium. Okay, so when there's a need for the muscle there to contract, calcium is released from the sarcoplasmic reticulum. Okay, and the calcium allows the actin, myosin, and ATP to interact, causing muscle contraction. So why does a muscle relax? The calcium returns to the sarcoplasmic reticulum. So in the presence of calcium, a muscle will fire. But then you see, I'm relaxing, the body will scoop up all that calcium back into the sarcoplasmic reticulum to save it for the next time I need to fire a muscle. Okay? Good stuff there at the bottom. Have a read of that. Perfect. We've got there's another video here. Again, here we're talking about, you know, the neuron sends a message down. Okay, acetylcholine there bridges the gap, the neuromuscular junction, which elicits their electrical cascade along the sarcolemma there of a muscle. And then you have these T-tubules that go down, these invaginations that go down, just to get that down into the deep part of the muscle. Okay? And then there you have your thick and thin filaments there. And again, great video. Have a watch of it. Can't play it. They won't. They'll copyright infringement. Okay? Good stuff. And again, another video, the same thing. Okay? And apologies there for the quality. Some of these here, are, you know, the quality isn't great, but it doesn't have to be to get it. Okay? So There's this video here, there's this video here, there's even that video there. Okay, so have a look at them all, get to know them all. They're kind of all dancing around the same thing, and gravitate towards one and get it. Got it? Good. Another one here. Great video. The whole idea there that the message coming there from the central nervous system. And you'll see, you can kind of zoom in here. Good video. And you'll see there that this is how the neuromuscular junction works. The neuron provides the message, and the message then gets cascaded onto the muscle, deep into it. The muscle elicits a response by contracting. Great video there. Pause it up, have a look. Somatic motor neurons. Somatic means body. Okay? So, skeletal muscle contraction only takes place when it is first stimulated by a nerve. I am going to give you the thumbs up. Okay, the nervous system sent the message. I did what I was told. I did what I was told. There you go. Somatic motor nerve supplies skeletal muscle, emerges from the spinal cord and travels there to the skeletal muscle there. Just a little bit of background information here. The whole idea of what is going on here. The electrical signal, the nerve impulse, travels down the nerve to the terminal and causes the release of the neurotransmitter acetylcholine. Okay, the acetylcholine diffuses across the neuromuscular junction and binds to the receptor sites. That's exactly what we were talking about right here. The whole idea of what's going on. So maybe you want to have this guy right here. Where are we here? See? I just like to play with my slides. So the acetylcholine there diffuses across the neuromuscular junction. Here we are. Stimulation of the receptor sites causes an electrical impulse to form in the muscle membrane. The electrical impulse travels along the muscle membrane and penetrates deep into the muscle through the T-tubule system. That's these guys right in here. Okay, there's your T-tubule system. Okay, that's how that electrical discharge gets deep into the muscle. The electrical impulse stimulates the sarcoplasmic reticulum to release calcium into the sarcomere area. So there's your sarcoplasmic reticulum, and it releases calcium into the muscle area, sarcomere area. The calcium allows the actin, myosin, and ATP to interact, causing cross-bridging. That's where those heads touch the fin. And ultimately, there for muscle contraction, this process continues as long as calcium is available. So when you get tired there, you basically run out of calcium. Muscle relaxation occurs when calcium is pumped back into the sarcoplasmic reticulum away from the actin and myosin. And when calcium moves in this way there, the actin and myosin cannot interact, and the muscle relaxes. Great little slide. I think I'll keep it like that there for next year. All or nothing rule. You know, the whole idea when electrical message travels down a neuron into a muscle, does the entire muscle contract or only some of it? Well, you see, it all depends on the neuron message strength. Okay? A strong or weak signal from the nerve will indicate how much of the muscle will fire. Okay? Meaning how much of the muscle fibers will contract. A muscle fiber either contracts 100% or not at all. So, depending upon the strength of the message coming from the nerve, that will determine the result of the contraction. If a little tiny message comes down the neuron, then you might get some muscle twitches, part of the muscle. A medium, you might get more of the muscle. A strong nerve message, the whole muscle will contract. Okay? So a weak signal causes fewer synapses to be involved, reaching fewer muscle fibers, weak muscle twitch. A strong signal causes more synapses to be involved, reaching more muscle fiber. This is what we call a strong muscle twitch. Okay. Impairment of the neuromuscular junction, there are neurotoxins. You know, if you get bit by a spider or something like that, it interferes with the ability there for the message to get from the nerve to the muscle. Okay? There's tetanus. Okay? There's botulism. That's a bad one. And if you open up a can of beans or soup and it goes psh, yeah, put that one in the bin immediately. You can read these here. There could be a question or two on the next quiz. Okay. Have a look at those. Have some fun. Okay. You'll see here with myasthenia gravis. Okay, you'll see what's going on. Let's go into it here. Let's have a look here. The symptoms there are caused by damaged receptor sites on the muscle membrane. Okay, the receptor sites are altered so that they cannot effectively bind acetylcholine. So basically where you're talking about here is, you'll see these receptor sites, they can't bind acetylcholine. So the message is coming down, but the muscle ain't getting the message. Okay, where did I go here? Curare there works by blocking the receptor sites on the muscle membrane. Because the receptors are occupied by the drug, the acetylcholine cannot bind with the receptor sites and the muscle contraction is prevented. Okay, and yeah, good stuff. Have a look at these there. There's your Curare, there's your Gravis, there's your botulism. Okay, you notice there the can of peas. Okay, you'll see what's going on here in botulism there. It interferes with the muscle contraction because unreleased neurotransmitter doesn't get across. Okay, there's your tetanus. Okay, excessive neurotransmitter release. And then you see there, locked jaw. Can't move your jaw. All right, good stuff. Moving on here, that's kind of the microbiology of muscle. Okay, and yeah, it's heavy. It's heavy. Now we're gonna get kind of into the macro. Like there's lots of different muscles here. I'm not gonna ask you to name all of them. We're gonna stick to the major ones. But these are good. They're good for a PSW course, good for a nursing course, good for general knowledge as well. All right. So, getting back into that muscle tone, muscle tonus. When muscles are relaxed, okay, no heads are touching the thin, no thick is touching there the thin, right? The muscle is relaxed. But some myosin heads are bound, okay? And some of them are bound and then they release. Other ones are bound and then they release. You know what I mean? It's just the whole process there of maintaining that muscle tone, because our lives could always, be in jeopardy at any given point in time. So ultimately there, these muscles are never 100% relaxed. Keeps the muscles there somewhat firm. This is what we call muscle tonus. Important there for preventing our muscles from overstretching. Also helps to maintain posture and balancing when we are moving. Muscle twitch. Single muscle response in which muscles contract and then fully relax. Tetanus. Sustained muscle contraction caused by repeated stimulus. Tonus, normal continuous state of partial muscle contraction. Just 3 good words there. You might see them again. Okay, so these 2 words here, which one are you familiar with the most? Odds are you're probably in this direction, hemoglobin, because you're familiar with blood. And the whole idea there that we breathe in oxygen. The air travels to our alveoli, which we'll all get into when we do respiration. The oxygen jumps from the air in our lungs across to capillaries there and into our bloodstream. Okay, and it's the hemoglobin within our blood, that iron. Okay, atomic symbol Fe. Okay, it's the iron there that allows the oxygen to bind to it, so that we can carry the oxygen and dump it off to all of our cells. Okay? Well, muscles have their own form of hemoglobin. It's called myoglobin. Now, if you think here, if you're just sitting here and a raptor just licking his chops and he wants to eat you, okay? And let's say you didn't have any breakfast. Oh my gosh, I don't have any energy. I didn't have a banana. How am I going to survive? Well, you see, your muscles, they have a storage tank of sugar and oxygen in them already. Okay, so in the case there that your life is in danger, you do have enough to get away. All right, you don't have a lot, but to think of it there as a 100-meter sprinter and a 400-meter sprinter. Yes, I just said sprinting and sprinting twice. 100-meter sprinter, 400, but they are completely different sports. And I mean like golf and football. Different makeups completely. Because a 100-meter sprinter, they don't go into oxygen debt. They run 100 meters. They utilize all the oxygen and sugar in their muscles. A 400-meter sprinter, though, after about 95 meters, you're completely depleted of all of your sugar and oxygen. So therefore, now you don't have any sugar or oxygen in your muscles. Your body will force you to go into oxygen debt. Okay, we'll talk more about that there when we get into white meat, dark meat kind of a thing. But muscles have their own form of hemoglobin. It's called myoglobin. And it's a storage tank for oxygen in our muscles in case we need it right now. So both are proteins there that contain iron. Hemoglobin is present inside RBCs and delivers oxygen to tissue. Okay. Myoglobin is found in the muscle and supplies with oxygen in stressful situations. So when there's a need, the muscles have an oxygen supply. Limited, but it's there. Now you think there that hemoglobin, it scoops up the oxygen from the lungs and drops it off to the cells. This myoglobin has a stronger affinity for oxygen. Okay, so the hemoglobin carries it around, and it has a strong affinity for oxygen, but not as strong as myoglobin, and that's why the oxygen will go to the myoglobin, okay, for storage. Hemoglobin has less affinity for oxygen as compared to myoglobin, so that the hemoglobin oxygen can dissociate and actually get into the muscles. Myoglobin has a greater affinity for oxygen than hemoglobin. It can scoop up that oxygen there. And so just as long as you guys know the differences there between myoglobin and hemoglobin. And I could spend 30 hours talking about the differences here, but I'm not. Okay. Energy sources there for muscle contraction. We've got metabolism there of creatine and phosphate, glycolysis. There we go. Anaerobic metabolism. And then we have aerobic metabolism. You'll see there, anaerobic, no oxygen. Aerobic, oxygen. Now you remember there from week 2, I think it was there, the whole idea, if the body is going to make ATP, it wants to be in an aerobic situation. The amount of ATP we can make from one glucose molecule is enormous. But in an anaerobic situation, we can also make sugar. We can also make ATP without oxygen, but we don't get a lot of ATP. But it works. There's over 600 muscles there in the body. The largest there is in the bum. Okay, I call this the gluteus maximus. Okay. Smallest muscle is the stapedius there in the middle ear. Okay. Longest muscle is the sartorius there, and that's from the hip all the way down, crosses the knee. We'll have a look at these there. You'll remember their origin and insertion. Okay. 3 parts there to a muscle. You have the belly, which is kind of the meat. You know, a muscle, it gets thicker in the middle, right? That's the belly. The middle of the muscle, the largest part during maximal contraction. The origin, the end of the muscle that doesn't move. It's the anchor, right? A muscle will pull. So this guy here is my anchor. This one here would be my insertion. This is the end of the muscle that moves, is involved in the contraction. Origin, insertion, belly. You'll see him again. 4 types of muscles involved in any action. So you have a look here. These are great words. I love them. The prime mover, or also we call the agonist. when we do complex movements, it is the main muscle that performs the contraction. Now, if I'm doing bicep curls, okay, so what is my prime mover? It is the bicep, right? That's the prime mover, that's the agonist. But muscles don't work independently of each other. I'm sitting here in my chair, but my feet are anchoring me, and my feet are about shoulder width apart, and they are, holding me down and, providing support. Okay? There are other muscles that are involved as well. So you'll see there that the bicep, in this case, is your prime mover. The opposite of the bicep is your tricep. Pull, push. And you see there, for every prime mover agonist, there is an antagonist. And this is the muscles that must do the opposite. Okay? Quadricep, hamstring. There are all these agonist, antagonist muscles where one does one thing, the other does the opposite, and together there they provide, this kind. They do what they need to do. Fixator muscles or fixation. These are stabilizers. Okay, and they allow the prime movers there to do their job. The whole idea there that the muscles of the back. And the back, there's lots of meat on the back. It's muscle everywhere, but there's different layers of muscle. Okay? And you have these little muscles there that are deep. Okay? They're involved in stability, stabilizing. And whenever you're picking up something off the floor, for goodness sakes, bend your knees. Okay? Never just, pick it up like this and you're bending everything there at your lumbar. You're in big trouble. You do that. You bend your knees, you get down, pick it up, and away you go. Okay? Synergists. They control, stabilize joints involved there for action there for the prime movers. So there are different muscles that are involved. Even though I am doing this exercise right here, my back is working, my lats, okay, my legs are holding me, they're supporting me. There are all these different muscles involved. So prime mover, agonist, antagonist, fixators, and synergists. Okay? Atrophy. Great word. Love it, love it, love it. Now, the whole idea there that the body's not dumb. If you're not using something, well, then the body ain't going to put any money into it. And if you're not exercising your muscles, well, then why would the body, we exercise our muscles there, okay? And when we exercise, and actually, Arnold Schwarzenegger, build muscle, what you do is, remember those muscle fibers, right? And when you exercise them, and you exercise them beyond their means, what you're doing is you're destroying those muscle fibers, all right? You've broken them. And then, you go home and you have a nice meal, you go to sleep. What happens there? The body it rebuilds those muscle fibers, gets them back. But because yesterday you broke them, the body goes, well, this guy's going to keep doing this. So you know what? We need to build more muscle to stop this. And then, the next time you do it, you exercise, you break them, build, and that's how the body builds muscle. Only if you're using it. The same thing with bone density. If you're not jumping around on your bones, if you're not exercising, if you're not providing pressure on your bones, well, what's the body going to do? It's going to remove all those minerals because, hey, this guy just sits around and watches TV 23 hours a day. He doesn't need heavy bone density, so we're going to remove. And it's the same thing, okay? So if you want to be a healthy individual, you have to use your muscles. You have to put pressure on your bones because then, therefore, your body will sense that you're putting pressure on them and it will maintain them. Got it? And if you do not maintain them, you will suffer what's called muscle atrophy. And I had that there in grade 10. I broke my leg in grade 10. I had a full leg cast on from hip to ankle there, the first couple weeks of grade 10. Yeah, grade 10 was a very great year. And anyway, at the end of 2 months there, I could literally put my whole hand down my cast, inside of my cast, because I had lost my quadricep. I hadn't used it in months, so the body's saying if he's not using it, then get rid of it. So then you have to rebuild that muscle again, right? But that's called muscle atrophy. There's hypertrophy, okay, growth in response to overuse, contracture, abnormal fibrous formations in the muscle there that freezes in a flex position. I'm more interested in atrophy. Okay, you'll definitely see that one again. This one here will, you know what I mean? And again, you don't have to memorize any of these, but some of these names here are whacked, all right? Some of the muscles are named on size, gluteus maximus, shape, your trapezius, okay, like a diamond. Orientation of fibers there, you got the rectus abdominis. Location, pectoralis. Okay, those are your pecs, your chest muscles. They can be based on the number of origins. Remember your origins. Okay, those are the immovable ends that do not move. Bicep has 2 origins. Tricep has 3 origins. This one here, sternocleidomastoid. Now you're talking muscles here around the sternum. Okay. Then we get into abductors and adductors there. We'll talk more about these there. You would have seen these there before when we were talking about muscle movement there last week. Okay. We'll get into these there. The more names there, they can be named by function. Have a look here. Levator scapulae raises the scapula. That's the bone on the back there. Okay. Extensor digitorum. The digits there are the fingers. We've got here, they can be named by attachment, merging of origin insertion attachment points there. We've seen that one there already. Sternohyoidus. Okay, that's the sternum and the hyoid. We just saw this one here. That's the sternum, clavicle, and mastoid process. Position or shape. Rectus femoris, straight. Serratus anterior, sawtooth. It kind of looks like that. External obliques. These here on the sides there, located outside with fibers slanting direction. Even some of them can be figurative. Your calf muscle is called your gastrocnemius because somebody somewhere along the line thought that it looked like a stomach. To this day, I don't see it. But anyway, your calf muscle is called your gastrocnemius. Trapezius there resembles a tablet. Those are in the back. Deltoid is the shoulder, shaped like a triangle. Delta. Let's have a look. Yeah, there's a lot of them here. Well, there's a lot more, but we're just kind of touching the surface. These are all good to go. I like most of them there. We'll have a look. Okay, and you'll see all of these. And, you know, when you're talking muscle, there's different layers, especially when you get over to, you look in here of the pectoralis. There's a pectoralis major and minor, but you get into the back. We'll show you there. Big, meaty muscles here in the back in different layers. Okay, we'll get more into these. We have 60 small muscles in our face, okay, which allow us there to make facial expressions. And you think here, remember insertion and origin, right? One part of a muscle is anchored there to a bone, and then the other part of the muscle there is anchored there to is attached to a bone there for movement, right? Origin and insertion. Well, you think here, muscles of the face. There's no bones. You can see here that the muscles are attached to our face. So in this case here, these muscles here aren't attached to bone. They're attached to our face to allow us there to move our face and make facial expression. It takes 40 muscles there to frown, only 20 to smile. So the whole thing, take a break and smile. You're only using 20 muscles. Frowning takes 40. Too much work for me. We're able there to make facial expressions because the insertions of many of the muscles are connected to our skin, not bone. Okay. Facial muscles are also used to chew. Okay. Open, close our eyes. Raise the eyebrows. Perfect. Facial muscles here. You'll see we got the frontalis, orbiculus oculi. Here we're talking eyes. Okay, levator, superioris, orbiculus oris, buccinator, cheeks, zygomaticus, platysma. Okay, and muscles there, the neck, and you have a look here. Okay, and your orbicularis oris is involved in kissing. Orbicularis oculi, there's your eye. Okay, and you have a look here and see how it all goes. Everything here is good to go. Muscles of the trunk, here we're talking about breathing, and I'm not going to hit this too hard. We'll hit this better there after reading week when we get into respiratory. Okay, but you have the intercostal muscles there, you have the internal, okay, and the external. And then there's your muscle there that's your diaphragm that's involved in breathing. Diaphragm is a bell-shaped muscle. At rest, it is a bell. And you'll see there when you take a breath, we'll get more into that as we go. Muscles of the trunk, abdominal wall, vertebral column. You just have a look here. These are the ones there I'm looking for. There's your pectoralis major, the big meaty muscle there on top of the chest. Underneath there you have the pectoralis minor. Okay. Deltoid, there's your shoulder muscle. Okay. External obliques on the outside. Internal obliques. Okay. Underneath you have what's called the rectus abdominis. Yeah. Good stuff. Muscles of the shoulder, girdle, and arm. Here they are. Okay. Oh, there you go. Oh, the formatting, eh? Rats. There you go. So please make sure to update that there in your PowerPoint. But these three muscles here are involved in the rotator cuff. Okay, supraspinatus, infraspinatus, and the teres minor. Okay. There's your trapezius. That's these guys back here. Okay, swimmers generally have these massive trapezius muscles. Okay. There's your deltoid. There's the posterior view of the deltoid. Infraspinatus, latimus dorsi. These are the big meaty ones here underneath the armpits on the back. Huge muscles, just like almost like just mats of muscle. Okay, latimus dorsi. These are the wings there underneath. Okay, rhomboids. These are in the center of the middle back there. Okay. Muscles of the forearm. Okay, wrist and hand and fingers. Don't want to go too crazy into these ones here because you know what I mean. Like there's over 600 muscles, and I'm going at you at 600. I'm going after any ones of these there that have been highlighted. Yeah. Other than that, don't really worry too much about it. Okay. I'm sure you guys have heard of this one there, carpal tunnel syndrome. Okay. The whole idea there that repetitive action can cause damage. And it doesn't even have to be, you know, swinging a hammer or, you know, doing heavy exercise. It can be just utilizing, you know, a mouse. And you're doing the same thing again and again and again. And you can hurt yourself for sure. Okay. Muscles there's of the thigh. These are the ones there that I want you to know. Okay. You've got your hip flexor. Okay. So it's major iliacus. Okay, you'll see them in there. Your sartorius, okay, longest muscle, all the way from the hip girdle, all the way down, transverses the knee and onto the tibia. Okay, quadricep, quad 4. Okay, so we've got these ones right here. So these 4 muscles there constitute the quadricep. Here we're talking the anterior leg, front of the leg. Okay. Posterior leg, and you'll see there's your glutes. Okay, biggest muscle there, all meat. And the antithesis to the quadricep are your hammers, your hamstrings. And you'll see there that we have these ones here. And you'll see the whole idea there that the quadricep if you think about if you're sitting in a chair, the quadricep extends the legs, and then to bring them back, your hamstrings, you can do hamstring curls there at the gym, and there again, you have your agonist, antagonist group. Okay. There is your stomach muscle, gastrocnemius. Again, I don't get it. I don't know why. Just, But anyway, and your soleus there. This one here, your Achilles tendon. You'll see there what goes on. It connects there, the gastrocnemius there to the calcaneus. Okay, remember that bone there from last week's slide? And if that ever gets cut, you can't walk. All right. And that is where we're at, and we're right on time. That's exactly where I wanted to be. And thank you guys so much for all of this, and I appreciate it. If you guys have any questions, just let me know. And yeah, I think we're in good shape. I'm going to stop recording now, and we're good to go.